Hello and welcome. So we were discussing about how to determine the symmetry of the normal symmetry type of the normal modes. So what we are going to do, we are going to take one particular example of this carbonate ion that we discussed in the previous class itself. So what we will do to start with, we will take all the x, y and z coordinates on sitting on each and every atom. Okay. So the atoms, the nuclei are to be in the origin, and then the corresponding x1, y1, z1 and or x2, y2, z2 and all this Cartesian coordinates will be there to act as a basis. So we have total 12 basis functions in our case. So now what we have to do, we have to form a representation based on this. So we have already learned that. So now we are going to see what are the the characters of the representation that we can form using these basis functions. Now when we will operate the by the way, so here we have differentiated each one of these atoms by giving numbers as 1, 2, 3 and 4. Okay, so the carbon atom is given the number 4. Now when we operate the symmetry operations on this basis function, what we will do, we will operate on the x, y, z, this this basis vectors, but not on these atoms. All right. So let's try to figure out what will be the characters of this representation. So identity will give me a matrix which is 12 by 12 and it is an unit matrix of 12 by 12. So ultimately all the diagonal element will give me 1 each and total 12 diagonal element. So I will get a character of 12. Now when I operate C3 on this particular structure, so what do I get? So C3, this is a D3H symmetry, right? So C3 is right here. So when it operates 1, 2 and 3, they shift their position by 1, right? So 1 will go here, 2 will go here, 3 will come here. So as we discussed earlier, this x1, y1, z1 or x2, y2, z2, x3, y3, z3 are not going to contribute anything to the diagonal. So this the fourth atom, that is the carbon atom, and its basis functions, that is basis vectors here, are of our use. Okay, and since this C3 is not changing this atom or is not shifting this atom, so these basis functions will contribute. So let's target one by one. So this, say I have the axis C3 axis along z axis, right? So what will happen? The z will remain as it is, correct? So it will contribute 1 to the diagonal. Now x and x4 and y4 upon C3 operation, what will be the total diagonal contribution from there? So if you look at that geometrically, you can easily solve for that. So we are not going to do that, but I can tell you that ultimately if you consider only these 3 basis vectors, because all the other atoms are moving completely, shifting, so we have to consider only this part. So therefore this whole thing boils down to a 3 by 3 matrix, right? So z will remain unchanged, so that will contribute 1. That is without any doubt, I can immediately write down. Now what will be the form of x and y? So if you solve it geometrically, you will see this will be something like this. Okay, because if you apply C3 on x4, it will give you minus half of x4 minus half of y4. So the other part will be root 3 by 2, and here it will be minus half. Okay, so this and you can figure out yourself. Okay, so therefore, if you look at the trace of this, you will have 0. So the rest of the 3 oxygens are contributing 0, and this one also, though they contribute to the diagonal, but overall sum will be 0. So you will get 0 character for C3. Now if you look at the C2, so say you choose one of the C2s. Okay, so if you can solve it for one C3, C2, then you automatically have the characters for other 2 C2 primes. So if you consider this C2 axis, then what you have, this O1 and C4, they remaining at their place, but O3 and O2 are interchanging. So we do not consider this. So we have now 6 by 6 matrix. So to start with, this C2 is along x axis, correct? So the x will remain unchanged. So I get a contribution 1 from here and 1 from here, right? So I get already a contribution of plus 2. Now this y1 will become minus y1 if I rotate along this x axis. So will be the fate for y4. Therefore this and this will contribute totally minus 2. So I have minus 2 contribution coming from the y side, and then the z side, z will also give me minus z1. So I have minus 2 contribution from the z. So out of this 6 basis vectors, I get total character to be equals to minus 2, right? So I can safely write minus 2 for all the C2 primes. Okay. Now let us consider the next symmetry element, that is sigma h. So what is sigma h going to do? So sigma h will not change any of the atoms. So everything is remaining their place. Now x and y constitute the plane of sigma h. So there is nothing going to happen to x and y. So there are total 4 such xy. So total 8 basis vectors will be contributing 1 each to the diagonal. So I have a contribution coming from the x's and y's. I have a contribution of total plus 8, correct, because nothing is changing. While the z, if you look at, it will be completely inverted. It will be reflected onto the negative z side. So all 4 will contribute minus 1 each. So therefore I have a contribution from z's to be minus 4. So the resultant of this is going to be plus 4, correct. So you have this one to be plus 4. Next is S3. So see, when you talk about S3 here, S3 has only one difference from that of C3. So C3 gave me this matrix, right, which is actually, this is the block in the total 12 by 12 matrix. So this 3 by 3 block gave some contribution to the diagonal, but ultimately overall this is going to be 0 for C3. Now what happened here, that is this z remained unchanged, therefore it contributed plus 1. So this plus 1 and then minus half, it together becomes 0. Now in case of S3, everything will be same except for the fact that there will be reflection in the xy plane, which will cause this plus 1 to be actually minus 1. So in case of, if I consider this C3, then say if I write in white color, it will be C3, then this is plus 1, and if I consider S3 in this color, then this will be minus 1. So when you consider S3, it will have total character to be minus 2. So I have minus 2 for this S3. Now we consider sigma p. Here also we can choose one of them. So let us take this particular sigma p. Alright. So this contains xz plane, correct. So what will happen to O2 and O3? They will be shifted completely because they are interchanging. So again I am left with this O1 and C4, correct, and their basis vectors. So since we are considering xz plane, then I have contribution coming from x's and z's to be +1 each, because nothing is going to be changed. So then I have 2 x's and 2 z's, so total 4, while the contribution from y's will be -1, because this xz plane will reflect this plus y1 to minus y1 or plus y4 to minus y4. So there will be contribution of -2 from the side of y's to the overall diagonal. So therefore I have 4 minus 2 equals to +2. So sigma v's will contribute +2 to the overall character of the reducible representation. So this is my reducible representation that I got using 3n Cartesian coordinates as my basis set. Alright. So what is my next job? So my next job is to reduce this, correct. So in order to reduce that, what we have to do? We have to use the formula that we have already deduced earlier. So if you reduce that, what you are going to get? You are going to get say, if I, so essentially I have gamma 3n equals to a1 prime plus a2 prime plus 3e prime, and you have 2a2 prime double prime, and you have e double prime. So this is what you will get ultimately. So you solve this, meaning that you reduce it, and then you are supposed to get this particular expression. So now I could find out what are the irreducible representations which to which all this my basis vectors x, y and z's transform as. So we have used 3n basis vectors, meaning that we have considered all the possible motions, translations, rotations as well as vibrations, and they altogether transform as this many number of this thing number of irreducible representation. So if you can cross check here, you will see these two are one dimensional and these e's are two dimensional. So 1 plus 1 2, then 6 8, and then again 2 10, and then again 2 12. So total dimensionality is 12, which matches with this as well as this matches with the overall number of basis vectors that we have used. So everything is in order. Now what is our job? We have to find out from this list of irreducible representation, we have to find out what are the irreducible representation that actually are for which the molecular vibration or the normal modes are actually the basis for. So how do we do that? That's very easy. So again you have to take help from the character table of the particular point group. So again we will resort to the character table of this particular point group D3H. So we have got our this list of irreducible representation, correct? Now what we have to do essentially, we have to strike out all the options that are for translation and rotational motion. Then the residual irreducible representation that we get will be for molecular vibration. So, if you concentrate on this particular character table here, the area 3 and area 4 for D3H, you will see that there are different linear functions that we have already discussed. So, now what we have to do? So, for translation, we have to look at the irreducible representation for which the linear functions, that is Cartesian coordinate x, y and z, they form the basis for. So, here if we look at, what we see is this representation E prime, for representation E prime, x and y form the basis together, while z form the basis for A2 prime, correct. So, this x, y and z, this forms the basis for translational motion. So, therefore, what we can write that out of this, if I go for say for example gamma for translation, so gamma TR if I write, then what we have E prime plus we have A2 double prime, right. So, I will again tell this part. So, in order to find out which irreducible representation will correspond to translational motion, if you have to find that, all you have to do, you have to look at the character table and particularly area 3, because area 3 gives you the linear basis functions x, y and z. Now, in area 3, this x or y or z, they will be written beside one particular irreducible representation or another particular irreducible representation, and you have to find out which representations they are. And what we saw, that this x and y together form the basis for E prime irreducible representation, while the z function transform as A2 double prime. So, if I take out this two part, I know that okay, this two irreducible representation they actually belongs to this, they are responsible for the translational motion, okay. Or in other word, actually this translational motion for this particular molecule, it transforms as A2 prime and E prime irreducible representations. Now, similarly, I have to find out what are the irreducible representation for rotational motion. So, again if I look at the character table and we look for the functions this Rx, Ry and Rz. So, we have to find out which irreducible representation you have this Rx or Ry or Rz, okay. Find out those irreducible representation and you have got the irreducible representations for rotational motion. So, if I look at again, we will see that Rz, that is rotation about the z axis, it forms the basis for A2 prime, all right. So, if I write gamma rotation to be A2 prime, and Rx and Ry, they transform together as the basis of E double prime. So, therefore, how many rotational degrees of freedom are there? 3. How many translational degrees of freedom there? 3. So, if you check here that you have total dimension of this is 3 and here also 3. So, that again tells you that everything is in order. So, I have found out the irreducible representation which correspond to translational and rotational motion. So, now if the altogether translational plus rotational, I have A2 prime, A2 double prime, E prime and E double prime. If I take out this 4 irreducible representation from this list, I have got the irreducible representation which which gives me the symmetries of the molecular vibrations, right. So, in order to do that, I have to get gamma. So I can write gamma vibration equals to gamma 3n minus gamma translation minus gamma rotation. Okay. So what do I have here? A2 prime, I have one A2 prime here, correct? So if I remove A2 prime from this list, so let me strike out this, and then A2 double prime, I have two A2 double prime, so I will strike one of them. Okay, I still have one A2 double prime, and then one E prime and one E2 E double prime from this list. So E double prime is gone, and then I have now I am now left with two E primes. So if I write that, ultimately what do I have? I have A1 prime plus 2 E prime, all right, and I have one A2 prime. How many number of vibrations normal modes we have? I have total 6. So the dimensionality wise I should have a match. So 1 plus 1 plus 4, total 6. Everything is in order. So these are the normal modes, these are the symmetries of the possible normal mode of vibration for CO 32 minus molecule. Now if you just go back to those structures that I showed, and I showed you the symmetries also. There I just wrote down, but how did I get this one is this way. Now if we have to suppose I do not know what are the normal modes, right? No one has drawn those structures, modes with the arrows particularly. Then how do I know which modes, which particular IR correspond to? So now what we need to do there. So if we look at the characters here again, so I have to look at the characters corresponding to A1 prime. So A1 prime has all the characters to be +1. So this is totally symmetric IR. So if I have to assume something completely symmetric about this molecular vibration, what can I think of? I can think of just a structure where all these atoms are stressed in equal amount in the same direction as that their bonds. Okay, so that means it's a symmetric stretching. So I can accordingly draw the normal mode of that, and then I have the characters for E prime. So E prime, what it has 2 for the identity and -1 for C3, while you have -1 for S3 also, and sigma v is 0. So in this case, I cannot comment on the exact stretching, bond stretching or movement of a particular angle, but it's not so it cannot be expressed in so pure form, but I can say some combination of bond stretch or combination of bond angle movement will give rise to this E type of symmetry. All right, and this A2 prime that has character of -1 with respect to sigma h, which means that that is not symmetric. This motion is not symmetric with respect to the molecular plane. That immediately tells you that this must be something related to the out of plane motion. Okay, then only you will have a negative character for this sigma h. So now, having said all these things, the next question is, like, could we come to this normal modes and their symmetries without dealing with all these coordinate systems x, y, z and all these things? So the answer is yes. So how can you do that? So you can do it by taking the internal coordinates into account. So how to do that? So you have to consider either certain bonds or the bond angles to be your internal coordinates. So here we can consider this CO bonds as my basis function, or this OCO bond angle as my basis function, or any dihedral angle even as my basis function. Now which one you consider first, or which one you consider later, there is no hard and fast rule. So you can start with any one of them. So for example, if I start with this CO bonds, then what we have, we can form a representation where my number of basis functions are 3. So so I can consider a set 1 which has 3 CO bonds. They act as my basis functions. Okay. So then on these 3 CO bonds, I operate all the symmetry operations of the 3H point group and I form the representation. All right, and then I reduce that. So if you form a representation where you are considering this only this, right? So these 3 bonds can either stressed in the same amount at the same time, which will be very much symmetric. So definitely that will be giving me totally symmetric irreducible representation A1. So here it is A1 prime, and the rest two, it can be like one is stretching in this direction and one is contracting. So there will be a combination of two motions. So I can intuitively can say that that will belong to one of the E representations. Okay, so call it E prime. So I can say that intuitively, and I can similarly form another set of basis functions. So let's call it as a set 2, where I consider this C3 OCO bond angles. Okay, so now unlike this CO bonds, I cannot have all the 3 angles being expanded in a same way. That is not possible. So therefore 2 angles will change, say, in the same way, but the other one will be in a different way. So again, in that way I can intuitively say that okay, I will have a 3-dimensional representation that I can reduce it to, say, one-dimensional and 2-dimensional representations, and that's how we can form the we can say or comment about the normal mode of vibration from the symmetry angles. So this particular part we will elaborate in our next class, where we will show that how using the internal coordinate we can exactly deduce the symmetries of the normal modes. Okay, so that's what we will deal in the following class, and then next after that we will go to the go and find out how to get the selection rule of vibrational transition. And I thank you for your attention. See you in the next class.